Hello, my name is Marko Gerbets, and I will talk today about modeling of the cross-crit infrastructure interdependencies, risk and cascading effects that are part of the ongoing Atlantis project. Atlantis project aims to enhance the resilience and cyber-physical safety and security of the key EU critical infrastructures. It is developing a set of risk management tools. Diverse tools should assist critical infrastructure operators in assuring the continuity of their operation in potential disaster situations. The presentation will cover the concepts and approaches used in managing the interdependencies among the critical infrastructure and assets. Agenda of the presentation is the following. First, we will explain the need to know the interdependencies among the entities of the system to understand its behavior under stress. Next, how to understand the dimensions of the interdependencies. Further on, how to start modeling the interdependencies within a system, and we will illustrate a possible start with an example. First, explain the basic terminology here. The interdependencies mean the connections among agents in different infrastructures in a general system of systems. Being dependent simply means needing the support of something or someone to continue existing or operating dependent on or upon something. Modeling means the activity of using mathematical models to make calculations or predict what might happen. Let's first try to explain the basic question, why modeling? Let us consider the system where the specific entities or critical infrastructures are somehow related within a larger context. Here we have an example of 5 critical infrastructures that are somehow related or dependent on a one-to-one basis. Thus, in overall, we visualized on the slide 7 dependencies. The nodes A, B, C, D, and A represent individual critical structures or assets. The critical structure's color could denote the type of critical structure products or services, for example. Arrows present one-to-one dependencies, and their color a type of dependency, for example. So the critical infrastructures can be mutually, for example, bidirectionally related or only unidirectionally. So the practical question here might be, what happens if the node C fails? We'll provide an answer to that question later on. So we need some modeling method. First, we need to define the system under analysis and its critical infrastructures. Next, we need to identify the specific dependencies among related critical infrastructures on a one-to-one basis and use the obtained information to anticipate the propagation of the effects of failures from the known threats. How do we do the modeling of the critical structure dimensions? Modeling of the system and its entities or critical infrastructures or assets requires first to understand their characteristics, foreseeable consequences if they fail, or severity if you want, and also the nature or the state of critical infrastructures operations and the environment in which they operate. They can be broken down to specific dimensions that we will present in the next slides. Here we explain a proposed approach to the modeling of the critical infrastructure's dimensions. The modeling of the critical structure's dimensions usually involves considering related subdimensions and property types as presented on this slide. Descriptions illustrate related properties. For example, infrastructure characteristics have some dimensions of, for example, its size in terms of part, unit, subsystem, whole infrastructures, and so on. Next, failure characteristics, cascading, escalating, etc., during which the state of operation of the failure occurred. And last but not least, the mental factors with possible effects like economic, legal, technical, political factors, and so on. Modeling of the critical structure's one-to-one dependencies next usually considers its main type as presented on a slide. It should be noted that presented types can overlap to some extent. Typical interdependency types are physical, where the state of the infrastructure depends on the material output of another critical infrastructure system. Cyber type, where state of infrastructure depends on information transmitted through another critical infrastructure system, and so on. It is also very important to understand how closely two critical infrastructures are coupled, meaning how quickly the dependent experience problems if its supply origin critical infrastructure fails, as well as how big the problem will be for the dependent in terms of its original performance or functionality. After acquiring information on the critical infrastructure's dimensions and their specific interdependencies among the critical infrastructures, we shall define also what kind of consequences we can expect if the threat or risk is realized. On this slide, we present some potential categories of the consequences of damages that might be relevant. Considering the critical infrastructure specifics, lost production, civil unrest, lost critical services, etc. might be the most relevant cases of measurable indicators. When the cascading effects realize, important is to understand how bad it can be. Failures in a connected system can trigger complex cascading effects. How far the disturbance will propagate, as well as how many branching can emerge and propagate in their own way. The proposed magnitude model presented on the slide considers them on a presented 6-level scale from the simplest to the most complex. For example, magnitude M0 denotes the simplest case where the failure of node C results only in a dependent failure of node A or the effect, and the scenario stops. However, the cascading effects within a realistic disaster scenario can be very extensive and complex due to potential escalation points. Here we present an example of possible approach how to start collecting data on the interdependencies among the critical infrastructures or assets in some case systems. First, each pertaining asset should be enumerated and named, and in simple words explained on its purpose, required inputs to perform, and on its intended outputs, etc. This exercise should facilitate the communication and understanding among the team members. Next, for each one-to-one critical infrastructure to critical infrastructure dependency, both the origin and the dependent should be documented and the pertaining dependency noted. It is also important to document the envisaged time and state of the dependent critical infrastructure that will experience if the source critical infrastructure fails. Now on this slide, we work on an example. We consider the slide 6 and its graphics representing 5 critical infrastructures and 7 dependencies. If we transpose the list of critical infrastructures to the matrix on this slide, we can precisely document, for example, type of the dependency that each pair, if any, in the respective cell. Let's list originating critical structures by the columns and consider dependent critical infrastructures by the rows. Note different colors of related headings to present the convention used. The matrix must comply with the list of the dependencies. Recall the template on the previous slide. In our case, we wrote down 7 one-to-one dependencies identified according to the arrows on slide 6. Now we can use the document to implement information further on. Documenting the critical infrastructure and the dependencies is only part of the work. For example, we can now consider the failure due to a possible accidental attack on one or more critical infrastructures. In our example, we consider that in that respect node C. In the first scenario step, node C fails. In the second step, nodes in D fail because they are dependent. In the third step, D caused the failure of A, and the fourth step, E should cause the failure of node C, but it already failed in the first step. The arrows present here a simple animation of the cascading failures propagation, covering 4 steps until it stops. Similar animation can be presented also over the map of the area. So, in our example, we consider a simple system with 5 nodes, 7 dependencies, and several failure paths that can be identified and studied. The approach also documents how the system works and allows additional considerations like what happens if node A or B fail. In the example, so we did not dig into closely related issues like time or speed of the failures escalation and what happens if the previous performance of the functionality of the node or the system. To summarize, we briefly explained the main concepts related to the meaning of the interdependency among the critical infrastructures, followed by the brief view on the modeling of the relationships among the members of the system. Understanding the interdependencies reveals relationships that are initially not so obvious but are essential to know and act accordingly. Documenting and modeling the interdependencies is a must for the effective critical infrastructure disaster preparedness.